This is Dr. Carroll, and today's video is about selection sort. Well, selection sort has two steps. First, it selects the largest unsorted item and swaps it into its correct place. Alternatively, the smallest item could be swapped into place, but we're just talking exclusively about the largest items. The next step is to select the largest unsorted item and swap it into its correct place. Or in other words, repeat number one. And we do this until there's no more numbers to sort. And that's it. That's why it's the simplest algorithm in my opinion. Let me give an example to help solidify things. So here's an initially random array, 71953. Okay, so now the task is step one, find the largest. Well, that's 9. And we're going to swap it into its final location. I've marked the sorted portion of the array with a horizontal bar to distinguish it from the unsorted portion of the array. Okay, so now we have 9 in its correct place. Okay, let's go on to the next iteration. We're going to find the next largest number, and that's 7. We're going to swap it into its final location, okay? And then next iteration, we're going to look for the next largest, and that's 5. We're going to swap it into its location. Notice each iteration, we are increasing the size of the sorted portion of the array. Now, when we do it this last time, we're looking for the largest. There's only 2. We find the largest. We swap it into place. And by virtue of that, we are left with the unsorted portion being of size 1. Well, an array of size 1 is, by definition, sorted. So then we're done. We don't have to swap that last item with its own. And so then the sort of the portion of the array becomes the entire array. And we're all done. So let's look at some skeleton code for this. So first off, we're going to set in a loop index variable I, and it's going to represent the index where the largest unsorted value will go. And so we'll iterate I from at the end of the array down to the second to last position, or index 1. And then we'll have a temporary variable here, the largest index, where largest index, as the name suggests, is the index of the largest unsorted value. Okay, now we need to find the largest value, and so we're going to iterate from the second position up till the end of the unsorted portion of the array. We've already taken care of 0 by assuming that from the beginning, initializing it before the array. And if the value that we're currently looking at in the array from the inner loop is larger than what we found previously, well, then we just set the largest index. Then once we found the largest index, then we're going to put it into its final place and swapping it. We'll swap array at index j with array I. Okay, and there's our skeleton code. Now, is this stable? No, it turns out it's not, because the swaps rearrange the values from their initial order. What about extra space? Well, yeah, it takes on the order of a constant amount of extra space. It just needs some temporary locations to perform the swap and the loop at indices. What about its big O? For its average case, it's n squared. Now, why is this? That's because looking at the skeleton code there's both an inner for loop that finds the largest unsorted value searching through the array, and an outer for loop that puts one number into the correct place, and it calls that n different times. So you have this nested loop structure, each one requiring about order n execution time. As you can see, it's only appropriate for small n. Well, worst case is the same. That it follows the same steps for the average and the worst case, which is why it is not adaptive. In other words, it does not depend on the initial order. Well, that's it for the selection sort video.